Welcome, everyone, to another episode of the Into Wonder podcast. Today, I have a very special guest. It is theoretical physicist Dr. Nathan Inan. I'm very excited to have this conversation. As I just mentioned, he is a theoretical physicist. He received his PhD at the University of California, Merced, under the guidance of the renowned physicist Dr. Raymond Chow. He is currently a professor at the school that I attend at Clovis College. Um, he's very, very much active in research, and he's published many papers that have been peer reviewed. And he often goes to conferences and gives talks and symposiums and all that stuff. A lot of his work has centered around themes of the intersection between quantum physics and relativity, and much other topics as well. He's even dabbled in neuroscience and a lot of the consciousness and stuff like that. So he's touched many topics. So I'm very excited to explore some of these today and just have some fun talking physics with Dr. Enan. So thank you for joining me, Dr. Enan. I really appreciate you being here.
Thanks, Antonio. It's a pleasure to be here. I'm very happy that you invited me, and I think it's going to be a lot of fun talking about all the stuff that you just mentioned.
Yeah, if you could sort of help us understand you better and where your curiosity and passion for physics really even stems from, um, could you share that with myself and the audience, where that passion derives from? And
Yeah, I'd be very happy to do that. So I guess I'm one of those individuals who just kind of came out of the womb, basically just knowing what I'm wired for, what I'm born to do, I guess you could say. Because, science, physics, astronomy, particularly when I was younger, were just so attractive to me. I was just really enthralled with how the universe works, looking at outer space and planets and stars, and then thinking about even things like atoms and forces and all of that. And so just even as a young boy, I was just very curious about how all of that worked. Um, I wasn't necessarily focused so much on academia. I'm probably not your classic super academic book nerd. Because I was just very much interested in a lot of other things like music, even just like pretty aggressive styles of music, as well as even like classic rock and hippie stuff. And I was into philosophy and probably things I shouldn't even talk about on this podcast. But I was just very exploratory, I guess you could say. I love to explore in all the different areas. But physics in particular captivated me the most, I think, for a variety of reasons. One is because I felt like it's the most fundamental description of nature at its core. So, the classic kid asking the parent, why does so and so happen? And then you give an answer. Well, then why that? And give an answer and why that? And you just keep asking why. I think generally if you are talking about the physical universe, you're going to get down to physics. Wherever you start with your train of questions, that's where you're going to end up. Of course, if you keep asking why beyond that, I think it really takes you to philosophy and maybe even theology and spirituality and things of that nature, right? Because then you start asking why as a sort of like philosophical question, not just how does it work, but why is it that way? And so it becomes honestly beyond physics in that realm. But physics I also loved because, or do love because it's also a, a combination of mathematical, rigorous, quantifiable, experimentally measurable study of the universe, as well as bringing in creativity and imagination. And, Einstein, I believe, is the one who said imagination is even more important than intelligence. And so just to be able to imagine and think of things that are beyond the scope of what we've normally experienced in our life is really what physics prompts you to do. Because we're probably going to talk about Einstein's general relativity, space and time, warping. We're going to talk about quantum physics and all the bizarre things that happen there. So a lot of that requires a lot of imagination and even goes beyond what even the human being can even really imagine. So those are probably some of the aspects, I guess I would say, of what got me into the field of physics and brought me to where I am now.
so it's that child that just never grew up and is still inside of you, just in
That's
the
true.
adult body.
Not gonna deny it. That's
I
true.
love that. It's so
That's
cool.
true.
So, what particular, as you started studying it more and more and understanding the different fields within physics and the different subtopics, what were you particularly uh, gravitated towards the most? No pun intended. What
Oh,
was
pun accepted.
pun? Yeah, what
Yeah,
really
no,
like, yeah, like resonated, and were you like, this is what felt the most right?
yeah, no, it really was. I mean, gravity was related. It was actually really astronomy and astrophysics that caught me the most initially when I was younger. I think just because planets and stars are just such extreme environments, and it's just so fascinating how, and I love color. I love the different, astronomy is filled with all kinds of different colors. I even use a
Yeah.
background for my Zoom that has colors, and so astronomy has a lot of that, and stars, planets, nebula, galaxies, all of that. The interesting thing though is that we obviously in life all have to find our path in one way or another. And so even though I knew my general direction was science and physics, I came to learn honestly that astronomy wasn't actually really what I truly found the most passion in, because I actually did my master's degree on a project that deals with astronomy. It was cataclysmic variable stars, which are basically like two stars that revolve around each other, and one of them is essentially consuming the mass of the other. There's like something called an accretion disk that's formed, where basically like the mass of one star begins to peel off and surround the other star, which is essentially consuming that mass. That's kind of just a colloquial way of describing it.
Hmm.
And it's a very good sort of project, especially, at the level of a master's, where you just have to basically, kind of just identify information, data, collect it, synthesize it, come up with a result, and move on. You're not necessarily introducing something brand new to the human race, or any knowledge that is completely revolutionary. But the point is, I actually discovered that wasn't for me, because it was just a lot of data collection, and I was really just much more intrigued. I came to realize with the fundamental physics and the theoretical aspects of how to describe our universe, not so much the collecting of data and sort of tabulating it and graphing it and then adding another, column to a table that already exists kind of thing. So that's kind of how my path went. And then I discovered general relativity was you mentioned gravity, there it is. General relativity was in my eyes, such a beautiful theory and very difficult to understand, and takes a lot of patience and a lot of determination. But as I continued to learn more about it, it just intrigued me all the more. And then I specialized even further in gravitational waves in particular. And that lined up with what was happening as far as in the field of gravitational physics. It was, I believe, 2014, which is right around when I was in my PhD, that gravitational waves were first officially detected by LIGO, the Large Interferometry Gravitational Observatory. And so that lined up very nicely. And then at the same time, I met my advisor, Professor Raymond Chow, who's very much into quantum optics. Well, he specializes in quantum optics, but he's also very much into gravitational physics, particularly gravitational wave communication. And so he looks at how to basically bridge those two. And that was just perfect. I was just like, that's where I want to be, like right there. That's right. That's right where my PhD needs to be. And so Ray took me on as a student, cranked out my PhD with him, loved it. One of the best experiences of my life, honestly. And I've heard PhD experiences can really vary. They can go from very painful to very fun. And I was very blessed that it was very fun. Finished that up, ended up then applying for my full-time position at Clovis College, which I love as well, because I do love teaching and I love working with students like yourself, has made it a lot of fun. So that kind of brings me to where I'm at here now.
I'm really curious because you kind of emphasized it a little bit when you were talking. How rigorous and what is it like to really understand Einstein's theory of general relativity in specific? Like, what really goes into that? Because I feel like even just to understand conceptually as a layman like myself, when you kind of like all these weird ideas of space-time
Hmm.
warping and all this stuff and like time
Hmm.
dilation, like it's like you can kind of like you feel like you understand it, but then to like really understand it through the math and to like see the beauty of his equations, how long would
Hmm.
you say does that take, and like how rigorous is that process?
Oh, yeah. Well, like most things in life, probably there's different levels, you might say, right? I mean, you can have a hobby, and then just depending on how far you go into it, you know, it will determine how much investment it's going to take, right? So I would say, if somebody, let's say, for instance, fresh out of high school, my son, for instance, is in his last part of high school, right? Going to go into his senior year. And I obviously chat with him. We talk about this stuff, and it can, a lot of this can be represented visually and with illustration, maybe even with a little bit of analogy as needed. And so at that level, you can actually appreciate a lot of what general relativity reveals to us, right? Gravitational waves being like ripples in a fabric, or black holes being this sort of like well, right? Or the Earth. Now, where it gets a little bit more abstract, it's interesting because even something as familiar as the gravity on Earth, mathematically, when you look at Einstein's field equations, general relativity, it actually involves the warping of time, not just the warping of space. So it gets abstract pretty quickly, even with something as
Mm-hmm.
familiar as just gravity holding our feet to the ground, right?
Yeah.
So then that's when you really do have to kind of, if you want to go deeper, the math will definitely play a role. Because if you want to understand why is it time that's being warped, like for instance, GPS systems, many are aware that they only operate if you take general relativity into account. And that's because time propagates differently up at space satellites in space than time propagates on Earth. And that distinction is mathematically quantifiable through general relativity, right? So it does get mathematical fast, obviously. I would say, like, let's say somebody has like an algebra background, you can kind of start a little bit because even Newton's gravity, which is buried in Einstein's gravity, is, you know, to some degree algebraic. If you have some calculus under your belt, that can take you a long way. Like, if we're talking about from 0 to 100, or 100 is like godlike understanding of general relativity, I would say with calculus, you could probably get a good like 50, 60% of the way. Then what happens is you have to really understand what's going on, you have to learn tensors. And are what go beyond the usual curriculum that even honestly a lot of physics majors ever see.
Oh wow.
So yeah, that so there's like a kind of like a cliff where like you can go so far, but then if you're gonna really delve deep, you suddenly have to learn tensors, and all of a sudden that's where differential geometry comes in, and that's where all of a sudden it becomes really tough to go further. And so that last like 30% of understanding costs you a lot more than that first like 60 or 70% of understanding. You follow what I
Mm-hmm.
mean?
Yes.
So I hope that helps paint the picture a little bit.
It does help. Like I'm really trying to get at too this distinction of like understanding like a theory from its conceptually versus like actually having that like rigorous understanding and like seeing the
Hmm.
math in actuality. Like what is that like as a physicist? Because I think that's a very special thing. It's almost like you have access to viewing this beautiful art form in like this particular way that like um us that aren't professionals can. So like what is that? What is it like as you, I mean you could use this theory or anything else for an example, but to like understand it conceptually and then start saying whoa, like seeing the way it works, like what is that like?
Oh man, you really are touching on something profound. What you described is just so accurate that when you learn the mathematics, even though, of course, admittedly, it introduces the challenges and the investment of time, but when you learn the mathematics and then you start to see how the math describes the physics or the physical world, it really opens your eyes to things that you just simply, honestly can't see and appreciate and be enthralled by at the same level if you're purely on the conceptual or visual, illustration. It's really true. And that's simply because math opens up the ability to describe things that go beyond what the human brain or the human experience is capable of. Because I'll just give you a very concrete example. Like in our daily life, spatial um, degrees of freedom, as we call it, consist of basically like left, right, up and down, and in and out, three dimensions, right?
Hmm.
And that's all. So I walk around the house, or I go upstairs or downstairs or into this room or that room. I'm walking in three dimensions, right? And then time is this sort of like from our daily life, it's this separate entity that basically always keeps ticking. You can't stop it. You can't change it. You can't speed it up. You can't slow it down. You're just like locked in and it only goes in one direction. You can't go backwards, right? And so it just feels like this like independent thing that you're stuck in, right? General relativity, the bizarre thing is mathematically it's one four-dimensional space-time where everything is all accessible just the same way, moving left and right, up and down, in and out spatially, is also temporally, in terms of time, time is just a fourth dimension that mathematically behaves that same way. I mean, admittedly, there's something called causality where you have to still respect cause and effect. And so there are some rules to the game. I'm not saying like all, that you can treat time totally the same as space in all ways. But the point I'm trying to make is that connecting space and time like that mathematically opens your eyes to the way the universe works in a way that you would not, I think, ordinarily be able to realize just from walking around and thinking about the world without the tools of math to help you. You know what I'm saying?
Yes.
So I hope that gives an example.
It does. That was beautiful. Gosh, yeah, it's just like I'm just sitting here, my mind is just like exploding. Like, these topics are just so interesting because you're right. We don't just like walk around and think, oh, I wonder if maybe space and time are a similar thing, or like we don't
Yeah,
usually
yeah, or
think and
like
like the.
connected into one fabric. Like who thinks like that, right?
Yeah, it's crazy. It makes me want to ask you another question, like hovering around this topic, like how do we scientists yourself come up with these um, thoughts that sort of like, I mean, that was a thought that Einstein kind of came to
Hmm.
him. Like, where the hell did that come from? Was it because he
Right.
had this rigorous understanding of physics and he was able to play with it a little bit, maybe,
Mhm.
and just kind of think like, oh my gosh, maybe time and space are something different,
Hmm.
like that. What do you think of like where that what would you call it? Like that moment of, I
Like
don't know, like this
revelation.
creative, yeah, that moment of revelation or like that creative
Yeah.
thought.
Yeah. Oh, that's a really good question too, because honestly, I don't think there's really only one way that this ever happens. Like technically speaking, they talk about inductive reasoning versus deductive reasoning. So sometimes things are deduced. Like for instance, the one you just mentioned, with Einstein and time and space and all that. In some sense, you could deduce and deduction meaning like, okay, if we have fact A and we have fact B, then that naturally leads us to fact C, right? That would be
Hmm.
deduced, right? Inductive reasoning is where you just kind of postulate, like, what if fact C is true? Then what else has to be true? And you kind of back up and say, oh, well, fact A and fact B would also have to be true as well, and it would all work together as a framework. So it's sort of like more of like this like bizarre intuition revelation and then you work backwards from there, right? So science has been done in both ways. It really has. So like if we continue with the general relativity or just relativity in general, there's general relativity and then there's relativity, right? Special relativity, how about that?
Special relative.
um Special relativity, right? So special relativity, even there, if you just simply identify that the speed of light is a constant no matter your frame of reference, like in other words, you say to yourself, okay, it doesn't matter whether I'm on a train and I shine a flashlight or somebody's standing off the train and they look at me shining the flashlight, both observers are going to say the speed of light is the same. That actually, from a deductive point of view, requires that you ultimately have to have the possibility that space and time both can be contracted and expanded. Because if you think in terms of, just one of the most basic physics equations is like speed is distance over time, right? And so if you're going to hold that speed constant and you're going to change the distance in the numerator, then you got to change the time in the denominator kind of idea. So there's this link, right, between distance, time, and speed. And so when you lock in speed as the speed of light, that leads you logically to distance and time being subject to stretching and compressing or enlargement or contraction, whatever, however you want to describe it, right? So that would be like a deductive thing, right? Where you could deduce it. But Einstein also had moments where he just postulated something and it was correct. He had a bizarre way of being able to do that. It was they even have a name for it in German. I probably will mispronounce it, but it's a Gedanken experiment, I think is what it's called. If have you heard of that
Yes,
that
yeah.
term, right? Like a thought experiment is how we would call it. He would do a thought experiment and it would turn out his thought experiment was correct. And boom, he just came
Yes.
up with like new physics. So, it happens that way as well, right?
Yeah. Yeah, it's just so bizarre. And it, it leads to this another topic that I wanted to talk about, which is this paper that Eugene Wigner wrote in the 1960s on the unreasonable effectiveness of mathematics in the natural sciences, where he just talks about how odd it is that math seems to describe phenomenon so accurately. It almost
Mhm.
seems like this universe is mathematical and there is some sort
Yes.
of structure to it that is not so arbitrary. What do you think about that? Do you think that the universe deeply there is some mathematics that rules everything, or do you think math just seems to work really well? What do you think about that?
That's really cool that you say that. And by the way, I haven't read that paper. Please send it to me.
I will.
So yeah, that's also a profound idea. Is mathematics somehow this like inherent framework that underlies all of reality, or is it just a tool we develop that helps us describe the universe? I honestly think I lean toward the first. That I think that, even if we were to get kind of spiritual or transcendental, and talk about like spiritually is our creator, God. I really do think in a sense, so I do believe that there is absolutely a creator. I believe there's God, and that God, being a supernatural, transcendent being, structured the universe with mathematics as like the scaffolding, if you will. And so then once that scaffolding was in place, everything else is just decorated around it. And so when you're doing theoretical physics, you're kind of going down into the scaffolding, almost like the Matrix, right? You're seeing the numbers. You're seeing the green number curtain behind everything, right?
Yeah,
So
yes.
what so yeah, I think that green number curtain is there. It's not just that we as human beings found it as a convenient way to describe the universe, but admittedly, it's an abstract question because, somebody could say, well, how do you really distinguish the difference between mathematics being fundamental to the universe and we, quote, discovered it versus mathematics being a tool that we use, that we, quote, invented, and we use it to understand the universe? Honestly, that's hard. That's like a philosophical, isn't that like a philosophical
Very
thing?
much
Like,
so.
it's
Yes.
almost like saying, does the rock exist because you found it, or did the rock already exist if you never observed it? Like, let's say there's a rock and nobody ever observed it. Like, does it still exist? If so, what's the proof of its existence if it's never been observed? And I don't mean by human beings, but even like observed in any way, like interact. If you have
Yeah.
something that has never interacted with the universe, like particle, you have an object, it's never interacted with any air, human, animal, anything. Does it, quote, exist in our universe? You see, it gets very, very tough to answer questions like this because it gets philosophical, right?
Hmm.
So I would be interested to see that paper because I wonder if he's kind of tackling that issue then.
I'll send it to you. I'll send it to you after this.
Yeah.
Did you come to this understanding that there must be a sort of creator of all this because like as you were studying physics, were you just like this is just there has to be there's no way that everything is this beautifully structured and that so elegant. Like there must be a creator of all of this. Is that where your belief in that comes from?
That was definitely a part of it. I would probably just add one thing to that, which is at one point I had a realization, not to imply it's some profound spiritual insight, but it just was a realization that came to me, which is that if there's anything that you cannot calculate, detect with an instrument, or perceive with your senses, then it's simply outside the realm of physics. And so it occurred to me, why should we necessarily um, conclude that all that exists is necessarily within the realm of physics? Like, in other words, is there a possibility of the existence of something or someone or entity or whatnot outside the realm of physics? And if so, that tells me right there, physics is not the be all end all of explaining everything. And I think that's the danger we run into with science, myself included, is it's such an effective tool that we just feel like, well, if that tool doesn't work, then whatever it is you're talking about is not relevant, because if I can't apply this tool to understand it and explain it, then it's useless, right? And I kind of understand why that happens, because I have a colleague, and he'll be like, well, look, if you can't detect it or perceive it or calculate it, you could just as well say that there are magical pink elephants floating, in this room. And if you can't see it, you can't perceive it, you can't detect it with an instrument, and you can't calculate it and predict it, anyone can say anything exists, right? So
Mm-hmm.
I admit it's a challenge, right? It's a
Mm-hmm.
challenge, but I think that's, so I won't try to solve that philosophical, puzzle here in this, podcast, or probably manage to do so ever in my life, but that's kind of what we're tackling, I think, in what we're talking about.
Yeah, it's something I think about really often too. I think I very much hold agnostic views, and I'm very just like in a place where like I don't know, because maybe humans need to conceive of this idea, because how could this just be so beautiful, but then it does feel very spiritual in that way. So I just feel like I'm in this like place where I'm like I just can't come to a resolution. Um,
Mm,
but it undeniably it's exceptionally beautiful, and it's really odd, and it's very mysterious.
yes.
And
Yeah.
it almost seems like, are we getting closer to understanding more about reality by doing science? Is it possible that we think we're understanding it correctly and we're going down the wrong path? Like it seemed like
Mhm.
Einstein's relativity explained uh, gravity in a way that
Mhm.
because Newton believe that time and gravity was just a subjective thing, and this is how it worked everywhere,
It
and
was just like a background that we're stuck in. There's no
yeah,
warping space-time. It's just a stage we live in, right? Yes.
yes. So
Yeah.
like, are we getting closer to something? Does it seem like we are, or are we possibly being led astray? Like, how could we even know that?
Honestly, what comes to mind is like the cliche that the more you know, the more you realize you don't know. And I think that really is fitting here, because I think what has happened is those pinnacle theories of physics, namely general relativity and quantum physics, just opened up this like Pandora's box of like madness, honestly. Like, as far as all that could occur, all that could exist, all that could happen. Punching holes through space-time to have a wormhole, and then what about quantum entanglement? And then, there's this notion that they could be described one and the same in the appropriate physics frame. You know what I mean? So it just opened up this huge just landscape of
Science fiction has
possibilities.
had a field day.
Yes. Yes. And honestly, science fiction becomes like science fact in a lot of ways.
It
You
does.
know? Like entanglement, the idea that like, or wormholes, or all, just all of that we just assumed was just fun sci-fi. And now we find more and more that the actual physics and mathematics allows us to describe these things. And in my opinion, and this might, be something we're going to talk about a little bit later, all of those bizarre ideas, at some point, we are going to arrive at a place where those things become absolutely engineered, applied, and a part of the technological advancement of the human race. And that's honestly what I'm working on myself right now quite a bit.
Yeah, I'm excited to get more into that, and the stuff that you're specifically doing. Um, how exactly? I mean, there's moments in history, for example, like staying on the topic of Einstein, where um, he comes out with this theory of relativity, and then all this just falls out of it. Black holes, like you mentioned, quantum
Hmm.
entanglement, all these really weird, bizarre ideas, quantum physics.
Yeah.
Um, do you think that most of these things that we find within the theories? Because your field is theoretical.
Hmm.
How do you separate between, you know, because I think Einstein also, I'm sorry, I'm going all over the place with this.
I think I know where you're going with this, though.
Like
Yeah.
Einstein didn't want to accept the fact that black holes could be a real phenomenon. He was like,
Hmm.
okay, I see that it works this way, but this is really
Hmm.
bizarre. Um, and like for example, string theory, like it, they, from what I've heard, it sounds like it's a very plausible theory, but we need a particle accelerator the size of the solar system in order to actually
Right.
uh, uh,
Test it.
clarify that, yeah, and test it.
Yeah.
So like,
Yeah.
how do you feel more comfortable with a theory than just like this is blasphemous and this is kind of out there, man? Like,
Yeah. There's a fine line between brilliance and madness, I guess you could say, right? I don't know if someone said that, but it sounds like a it sounds like a saying that should exist, right?
it does.
Um, no, but you're absolutely you raise a really good point because in theoretical physics, the difficulty is that the mathematics allows for more to occur than what we actually necessarily observe. That's what I would probably say in response to what you're talking about, because like you just said, for instance, general relativity predicted the possibility of a black hole. Although I would just put a little disclaimer on that. There are actually ways that you could predict the possibility of a black hole that didn't even require general relativity. It's just that
Mhm.
general relativity formalized it on a level that made it so that it was all the more convincing from a theoretical point of view that they must exist. But there's other ways to get there. But the point, though, is that you're right. Not only with black holes, but with gravitational waves, by the way. That Einstein also went back and forth on whether those exist, or was it just an artifact to the mathematics? You see, what makes it tough with general relativity is that there's what we call coordinate invariant observables. In other words, if you're going to say something happens in the universe, it should not depend on your coordinate system. And so, like for instance, like if a particle's cruising by, right? And you have a coordinate system in front of your face, and you're like, okay, here's my x-axis, and now that particle is at x equals 1, and then x equals 2, and then x equals 3, and then so on as time proceeds, and you're like, okay, that particle's in motion, right? Well, what happens if you take your coordinate system and you move it along with the particle? So let's say when the particle's sitting at x equals 1, now you all of a sudden boost your coordinate system so that the particle's always at x equals 1. Now all of a sudden you ask the question, did the part does the particle have motion? Well, not according to that coordinate system. It's stationary. It's stuck at x equals 1. You see how like why the mathematics can sort of trick you in general
Mhm.
relativity? So
Mhm.
I'm giving you just kind of like a very basic idea of why that's tricky. So on a more advanced level with gravitational waves, it introduces the question, are there really truly physical waves propagating through the universe, or are they ripples in my coordinate system? So is my coordinate system ripply, wavy, right?
Mhm.
And that will lead you to, think that there are gravitational waves when really maybe physically there aren't. So anyways, I'm just definitely like agreeing with you on the fact that yes, mathematics can predict things, and it leaves this challenge of, is that really a physical thing? Or is it an artifact of my theory? But interestingly, it goes both ways. On one, I've been talking about the possibility of the math predicting something that maybe does or does not exist. There's been other things where the math predicted something, and shockingly, it was expected it absolutely doesn't exist, and it did. Consider Dirac, for instance. Let's
Mhm.
go into the quantum realm. Dirac, when working out the Dirac equation of motion, discovered that there were particles with positive and negative energy. And that was problematic because E equals mc squared, and we know the mass is positive, so how can the energy be uh, negative, right? You have to have positive mass, positive energy, negative mass,
Mhm.
negative energy. And we never observe negative mass, by the way, right? But it turns out if you continue going deeper into the theory, you find that those negative energy states actually describe antiparticles. And those antiparticles have been absolutely observed to exist. It's real. In fact, it's funny, I just saw a YouTube video where they're like making antiparticle or antimatter, and that stuff is like insanely expensive. It's like I don't know what it was, like trillions of dollars per gram or some absurd, don't quote me on that, but it was just insane. But anyways, the
Wow.
point is that, the point is that it's real. Like we create, we produce it, we capture it. It can be literally sold if you want. You see what I'm saying? Now,
Yeah.
I would love to see the day we can like make black holes and sell those. I don't know how that's gonna go, right?
Yeah.
You know. But anyways, the point I'm trying to say is that, you raise a really good point that mathematics alone is not enough, and that's where experiment and observation has to come in. And this is the classic duality of fundamental science. You have to have your theory and you have to have your experiment. You can't have one or the other. You're not going to properly understand the universe. And like you said, some theory. So the question right now for the human race, as far as the, progress of fundamental science goes, is which one has moved ahead of the other, theory or experiment? And I think it's theory, because you just stated it yourself. You said string theory, for instance, is an excellent model for describing the unification of all of fundamental physics, but you can't test it, at least not, in our possible technological means, right? So then it leaves you wondering, what value does it really have at that point? It's just math at that point, right?
Right. Exactly. Yeah, that's hilarious what you said. Like you could just people are bottling up this stuff. You know what I should do? I should bottle up. I should get some mason jars and say that there's dark matter. You can't see it, but trust me, it's in here, and just ship that.
Yeah,
And I'll
snake
just
oil. I bet you
um
anything. The sad thing is somebody out there would buy it and show it to their friends, and
they would.
and then I found, I've got a bottle of dark matter here. Maybe somebody will want to drink it, see what it does. Now, antimatter, I would not recommend consuming that because it annihilates with regular matter and turns into pure energy, and a lot of it.
Wow. Who would
Yeah,
even
that's why it's so
buy that and
expensive.
what for?
What's that?
Who would even purchase that and what for? Like these
Oh,
multimillionaires that are.
yeah, well, if you think about propulsion technology, so that this also segues a little bit into some of the stuff I work on. Propulsion technology, because if you need a very compact fuel source, presently, the most compact fuel source we have is nuclear energy,
Mm-hmm.
right? But that's very difficult. You have to detonate it, right? You have to have, like, the equivalent of an atomic bomb or a nuclear reactor or something like that. And so it's quite the undertaking to be able to access nuclear energy. So it's very difficult. But if you have some antimatter, Ah, throw it into some regular matters, stir the soup, and man, you've got more energy than you could ever utilize for anything. You see what I'm saying?
How do you even get antimatter? Where does that come from?
Well, with particle colliders, quantum
Mm,
mechanically, statistically, literally any kind of particle can come out of a quantum particle collision, scattering. So I won't pretend I know the details. I honestly don't, but I do know that that's why antimatter can exist, is because if you energize the vacuum, I mean, that's essentially what a particle collider does, is it basically just dumps a tremendous amount of energy into the vacuum, and then what spits back out from the vacuum is every kind of particle, like all these particles, pop out. And then basically, I don't know where they go from there, but I do believe they use magnetic fields, I think, to capture and to isolate, because they have to stay isolated. Because remember, you can't just put it in a jar, because like it can't interact with regular matter or it annihilates, right? So I'm pretty sure that's broadly speaking how that works, but I wouldn't be able to elaborate beyond that, quite frankly.
oh yeah, I wish I could get my hands on it and just that would feel very I don't know, I feel like I would just be like some mystical being. Like I mean like I got
God-like
antimatter on me.
being.
Yeah.
Yeah,
Yeah.
until like until the government comes and takes it from you,
Until they
right?
come
But
and take it from me.
that's a political issue, I guess.
Yeah, it
But
is.
but that really is a relevant thing, because some of the stuff I work on, um, we worry about government getting involved. Like there's black projects, and then I don't know if you know, like I was learning about how there's certain government policies that actually, if they conclude that you have a certain technology that is a danger to the country, or like a security concern, that they need to have possession of that for the benefit of the country, there's actually policies in place that permit the government to take that from you.
No way. Can you share a scenario that you've been in
Oh,
recent like on YouTube?
I've never been in it, but I am working
Okay.
with a company that worries about it. So, I'll give you just a little tidbit about it is I'm working with a company named Texas Space, and
Hmm.
we're really focused on just very cutting edge breakthrough technology kind of stuff like gravitational propulsion is a big one that's out there that people are trying to figure out how to engineer gravity, because if you can engineer gravity, oh, there's so much you could do that would just absolutely turn everything upside down as far as technology goes. C- Transportation, as far as, or I'm talking about like I'm talking about like, galactic travel kind of stuff,
Wow.
right? Because yeah, and then communication, if you can use gravitational waves instead of electromagnetic waves, that would be huge. So the point though is that as I work with this company, um, and we seek funding, we have to sort of debate like, is private funding the way to go? Like millionaires and billionaires who are trying to have a hand in this pot, and that's the way to go? Or should or is the government the right way to go? Like if you think about the Manhattan Project, like the atomic bomb, all the resources that went into that. So when the government gets involved, then you have, so you can put it this way. The government's this like giant pool of resources that would exceed drastically any private party, but you are now at the risk of the government now essentially taking control of your project if it deems that it's a security issue. See what I'm saying? So it's like a double-edged
Yes.
sword in a sense,
Hmm.
and could militarize it. So then that brings in the moral and ethical aspect also, right? Because this same technology I just described with gravitational engineering, you could generate like a gravitational beam, like a energy beam that could basically punch through literally anything, absolutely
Yeah.
anything. So at that point now, once that, and if you think about it, that's exactly what happened with E equals MC squared. It didn't take long before it turned into an atomic bomb, and all of a sudden you've got 70,000 people incinerated with a single blast because of a very simple equation, E equals MC squared. You see what I'm saying?
Yeah, it's dark when we take these scientific advancements to use them as like a power thing
Right.
into like it's.
It's
I'll just
true.
do
It's dark. But I mean, like, to be fair, and I'm not like a historian or super knowledgeable, but you also have to ask questions, these are moral questions, and I don't pretend to have the answer. But like with World War II, for instance, it's I've heard it said many times by people much more knowledgeable than me that if the atomic bomb had not been used, many more millions of people would have died
Yeah,
for that war to come to an end. You know what I mean? So then it's tough. Like, I don't want
definitely.
to be the one to have to call the shot on stuff like that. That's all I know. But I have to admit, it's not a clear-cut thing like, oh, just, no atomic bomb, that's bad. Like, no, the reality is like millions and millions and millions of more innocent lives, people who aren't even in the military would have died. So how do you, those are tough questions, right?
Yeah, I feel bad that scientists have to be semi-involved. I remember in the movie I watched, Oppenheimer, it just seemed like
Right.
he was like he didn't know how to feel about it. He was like, "Oh, this
Mhm.
is." I don't know if that movie's historically accurate, but he just seemed very disappointed
That
and
aspect I
very,
think is, yes.
wow.
Yeah. And Einstein also was torn because he also wrote a letter, if I recall correctly, to the president, like
Yes.
basically saying, like, look, your enemy's producing a nuclear weapon, and if you don't do so first, it's not going to go well for the
Yeah.
world, literally, right? We'd be speaking a different language right now. And we might not be treating other civilizations well,
Mm-mm.
you
Yeah,
know?
it's I agree with you. I would not want to be in the position saying, "Well, who needs to be wiped?" Yeah, that's
Right,
totally fine.
exactly. Yeah, I really don't want to be in that position either. I'm not cut out for that at all. Like, I love the science, and I know those moral decisions have to be made, and I'm glad that they are being made. I wish they didn't have to be made. I wish humanity would just, function in a way that such choices don't have to occur, but sadly, it's not the world we live in, right?
Yeah, it's mm, worst part about
So,
science, in my opinion.
the
Um,
dark side.
the dark side. Let's get to the fun stuff, though. Let's get back to the fun stuff.
Hey,
Um,
every movie has to have a sad scene, so there it
yeah,
was, right?
there it was. I'll put some like sad piano music over it or something.
That way the final climactic ending is all the more, exhilarating.
Yes, yes, it's a melodrama. Let's get into some of your research.
Yeah.
I want to talk about it, but when you explain it, and I know I'm asking a lot of you to do this, but if you could try to portray it in a way that is to the layman in like semi comprehensible. I know I'm asking a lot of you to do that, but if you could kind
No,
of
it's
talk
all
about it and share that with myself and the audience, I would love to hear about it.
Oh, thank you. I would love to talk about it. Yeah, and honestly, being a teacher, I think it helps because I'm very much aware of the need to reach audiences that are not necessarily technically informed or trained and such. Um, the research I've worked on personally, and I'm not by any means at the level of, you know, uh a lot of my colleagues, honestly, who have like dedicated, I tend to be a little bit more diverse in the sense that like I love my family and I like my marriage and my children and I like to teach and I like hobbies. So physics is not like my be all end all. There's some people who like literally eat, sleep, breathe physics, and that's
Mm-hmm.
like you know what I mean. Yeah, Einstein was one of those, right? You know what I mean? Like, the marriage didn't go so well, and then he married another one, and she pretty much just she was just good as long as like she brought him food and left him alone in his basement. Like they had like a dysfunctional functional thing going on, right? Where she got to
Yeah.
be Miss Einstein and he got to have somebody take care of the laundry and the meals and focus on physics. Anyway, so my only
Yes.
point is that like I love to share what I do, but it's not all that I do. But anyway, so within what I do, I have had the privilege of working on a diversity of projects. So I already mentioned the gravitational wave stuff, and that was like my first kind of my first love from a scientific point of view, what I did for my PhD and what I continue to still work on now. And that is probably one of the more practical aspects of what I've worked on in the sense of uh, we look at laboratory scale experiments. I literally was just working on the paper right now before we hopped on this podcast together. So it was a what's called a Hertz-like experiment. Hertz came up with a way to communicate electromagnetically from a transmitter to a receiver, and that was a
Mm-hmm.
breakthrough in communication technology. We're attempting to do the same thing, but with gravitational waves. And the difference, the pros are that gravitational waves can practically go through anything. So you now no longer have obstructions. You don't have interference from, barriers. You don't have to worry about the problem of your cell phone not getting reception or any of that. That's all you don't even need satellites in space anymore. You can just send a signal straight from, here to Japan, because it just
Wow.
goes right through the earth, no problem, right? So it would really make a difference there. The cons is that gravity is so weak. It's actually the very same reason why it goes through everything. It's so weak that to get a detectable signal is extremely difficult from a engineering standpoint. And so you have to try to generate the largest signal you can. You have to have the most sensitive receiver possible. You got to play all these games. And I'm not an experimentalist, that they suffer even more than me. For me, I just have to work on the equations and come up with the numbers and get something in the ballpark. And then they have to deal with the thermal fluctuations and acoustic fluctuations. Anyway, so that's the more practical side of stuff I've worked on. Other things I've worked on are a
May
little
I
bit
ask
more.
you? May I ask
Yeah,
you
yeah,
about that
yeah,
previous work?
yeah. Please do. Go
Um,
ahead.
in regards to gravitational waves, how are those detected? Because the only way I know that they're understood is, as you mentioned earlier, LIGO, that
Yes,
long laser beam they have, and
yes.
from when black holes merge somewhere in the universe. Are there other ways to detect gravitational waves, or is that the only way?
In principle, there are other ways. So the main thing that, as you just mentioned, is a very important point you stated: black holes and neutron stars and very, very incredibly mass dense objects moving at immense speeds, what we call ultra relativistic. Uh, you know, uh, very small fraction of the speed of light, nearly the speed of light kind of stuff. So such extreme sources that even though they're very, very far away, which that does diminish, of course, the signal by the time it gets to us, but because those sources are so insanely powerful, that signal is still sufficient that by the time it gets to the Earth, the apparatus, like at LIGO, you mentioned a very large laser, for instance, is sufficient. But even there, it was quite the technological feat to get down to what they call quantum limits of observation, where literally the only thing left that they isolate everything, thermal out, acoustic out, like everything out. It's all noise is eliminated. They even talk about like if if a truck drives by, like who knows how far away, like the seismic activity, associated with just like something like that could disturb
Wow.
the experiment if it were, so it's just
It's
ultra,
incredible.
ultra, ultra sensitive experiment that achieved the detection, right? Now, the challenge is that in a laboratory, you don't have the luxury of neutron stars and black holes to play around with to produce your gravitational waves, right? You're dealing with energy levels that are like many, 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 many orders of magnitude smaller, right? So then you do have to come up with more unique ways of sensing the signal. So with LIGO, it's the simplest way I could put it, it's a couple mirrors and they move relative to each other. And when they move relative to each other, that impacts the way that the laser propagates between them, and that can be detected. That would not be the way that you would do this in a tabletop experiment because it turns out the longer your laser path is, the more sensitivity you have. So LIGO is like miles large. But if you're gonna have a cell phone, you don't have the luxury of a miles long cell phone. You see what I'm saying? You're talking about centimeters, you know what I mean, kind of stuff. So in that case, you have to come up with other ways of sensitivity, which would get a little bit more technical. But yeah, it does require playing around with other ways of detecting gravitational waves besides the way LIGO has been doing it.
Yeah, what a beautiful engineering accomplishment. I mean, wow,
Oh
that's
yeah, it's so
that's
true.
insane.
That's so true. It really is. I would say LIGO and CERN are like the two. Honestly, I hope one day I
And the
get to
James Webb,
visit. Oh, is that the array of telescopes?
that's the one that gives all the like the really nice photos of galaxies far away. I think
Oh,
that
is
got the
that
cosmic microwave, or was that the Hubble that got the cosmic microwave
the
background?
Hubble? Yeah, the Hubble, of course. But you're not going to get to visit that. So, yeah. But no, you have a good point. You have a good point. There are some other very exquisite ones. I think I was thinking about ones that like I would love to actually go see one day, right?
Oh
So
yeah, yeah,
so LIGO would be one and CERN would be one. Those are like
yeah,
tremendous human achievements that you could actually go in like awe at.
yeah. That
Yeah.
is so cool.
So that's
Um,
one aspect of,
mhm.
and then I've worked on dark matter, dark energy, superconductivity, and then general frameworks that, quantizing gravity. I think, I've worked with, some of the students even at our college. We looked
Mhm.
at some, aspects of quantizing gravity. So as you can see, it's more and more theoretical, like more and more fundamental, and less like tabletop experiment type thing.
Mhm. How do you go about research usually? Is it I mean, I'm sure it changes throughout. Is it usually an idea? Is it a maybe a colleague represents an idea, or ideas get thrown around in the inbox, and you're like looking through them, and you're like, no, no, no. Ooh, that one's cool. Like, is it like how
Like a
does it work
buffet
usually?
of
Yeah,
like
yeah,
what do I want to put on my plate today?
yes,
Um, yeah, honestly, that's evolved because I'm sure it's absolutely no surprise to you that AI has obviously been a game changer, right?
yes.
So I would say when I first started this out, so I really actually am extremely grateful I've had the opportunity to sort of live in an era where we kind of went from pre-AI to now, AI being a significant part of research or life in general, and who knows what the future obviously has. But the point I'm is that in the past it would be I would look at other papers, so it'd be a combination of um, papers, ideas that just come to my mind while I'm just walking around, and I'm like, oh, what about if we did this or did that, right? Or honestly, interestingly, during the time of falling asleep or waking up, and I've kind of heard a lot about this and learned a lot about this that the state that your mind is in that sort of like semi-conscious state, it has the freedom. I don't want to pretend like I can explain all of this, but I can just elaborate on like what I've experienced and how it matches up with things I've heard that your brain obviously is in a different state when you're in different periods of the day or different circumstances, right? and
Mhm.
and the whole so I in fact I don't remember the name of the individual, uh, um but there was a person who would hold a steel ball, I think it was, And he would sit on his rocking chair, I think it was something like this, unless this is like a Newton's apple type story, but I'm pretty sure there's some
I've
accuracy to
heard
this,
this. I've heard this too. Maybe it was
right?
from you. I don't know. I've heard this
Oh,
before
okay.
though.
Yeah. I don't know. I think it was like Edison or Franklin anyway, one of those, inventors. And when he would be like falling asleep, I guess like his hand would obviously like, weaken, and then he would drop the object and it would kind of alert him again. And then he would awaken with a breakthrough idea, maybe whatever problem he was working on or a new idea. And so he was capitalizing on this like semi-conscious, and I know you like neurology, so I figured this kind of goes down your avenue. But he would capitalize on this like semi-conscious sort of nebulous state of mind and bring it into his conscious life, because that's, the idea would come and then you would sit down and actually like work it out in detail. You know what I mean?
Hmm.
So a lot of that. But now, honestly, with AI, sometimes a question comes to my mind, pop it into chat. I might not even be at my computer. I might just be literally like at the grocery store. I'll just be like, oh, what if dark matter and dark energy are unified actually? I mean, obviously, I'm a bit of a nerd. So who thinks about that while they're picking up their cereal or their milk? You know what I mean? Anyways, but,
I
and
love
I'll
that so
just,
much.
I'll throw it into chat, and chat will just like crunch. I mean, just the efficiency is amazing because it can look up tons of papers, figure out what already is known, what's speculative, how your new idea fits in, what would the mathematics for all of that look like. Stuff that would take me easily like 3, 4, 5 hours to reach is seconds. It's 3, 4, 5 seconds, maybe a minute or something like that, right? So it's
Wow.
just drastically increased the ability to innovate, I mean, I know that
Hmm.
there's a lot of bashing on AI for understandable reasons because people use it as a crutch and things like that. But I'm just very grateful, like I said, that I had the opportunity to be trained honestly without it, because then I have both sets of martial arts. You know what I mean? So if
Hmm.
tiger style is not going to work, they go monkey style. I don't know if that's a real
Yeah,
thing, but
yeah, yeah,
But if you only grow up on monkey style, you're never gonna learn tiger style, and that's it.
yeah.
I'm making this up. I don't even know if that's a real thing. I probably just watched Kung Fu Panda too many times.
I think I think what you said though, I think that is important that you were able to have the tiger style, the separate one without it, because I think a lot of people like in my generation that are in college right now, I think are going too reliant on it, and I can see that just like,
Yes.
ooh, this is going to be so bad. Um,
Yes.
so
Yep.
that's definitely
That's
there.
so true.
Yeah. What do you what like? Because I think about this a lot when I'm using AI to help me with understanding a concept or mathematically or whatever it may be. How often do you run into limitations where you are like, okay, well, it can't quite explain this, or it's not,
Mhm.
they can't, it's very good at doing this, but it, uh, it goofs up a lot in this area.
Yes. Yeah. It's really, again, like anything in life, it's a skill working with it, because the more you work with it, the more you realize its limitations and how to properly navigate it. So like your prompts, for example, is a huge part, right? You have to, if you prompt it a particular way, like if you just say, tell me, I'll see, so there's like a colleague who sends out emails. He loves sending out emails about his Grok usage. And I noticed that his prompt will just say like, explore dark energy ideas or something like that, right? You know what I mean? And then the output is only as good as the input in a sense. And so then, yeah, it's going to talk about a bunch of dark energy ideas, but it's not going to be nearly as effective as if you had said something like, say, for instance, general relativity predicts that there's, expansion of the universe. Tie that in with dark energy, give me the equations, derive them rigorously, show me exactly the assumptions involved and what already exists in the literature and what new contribution would be possible for me in that area. You know what I mean? So like if you're really um working with that tool effectively, you'll get a whole lot more out of it.
Hmm.
Now, some shortcomings I've noticed though are it's very much a literal machine, in the sense that, like, say for instance, you make a mistake writing something up, and it says like oh, you accidentally treated the photon as if it has a rest mass or something. You're like, okay, fix it by taking that out, right? And then it'll pump out a new section. And in that section, it'll say like, here's how we're going to do the derivation. We are not going to treat the photon as having a rest mass, but the reality is when you write a paper, you're
Mm.
not going to put that in your paper. You know what I mean? So
Hmm.
so it's kind of clunky. You got to edit it, right? But the probably the more important one, this is probably the most important, is that you have to remember that AI is collecting information from what is known already in the human race. And if you're a researcher, you're trying to go beyond that. So sometimes it actually binds you up because it'll keep saying, no, you're wrong, no, you're wrong, no, you're wrong, simply because what you are coming up with is beyond or outside of what the human race already knows. And that's what AI is trained on. So you have to
Hmm.
be able to navigate that. Like I kind of view it as like you reach this saturation where you use it on a certain topic, and then once you feel like you've gotten all you can out of it and you're just arguing with it, then you just leave it alone and you decide whether you're going to just still stand your ground or whether maybe it helped you realize something really truly is wrong that you're. So you see how it's like it takes some balance.
Yeah, I love that you mentioned that. I think that's really important for our listeners as well, and people that are in STEM field to like keep that in mind when they're engaging with AI, especially like trying to come up with some idea, that it is just this amalgamation of information, that it's not this
Mhm.
creative genius that's going to come up with quantum gravity if you asked it. Because I've
That's
asked it
true.
and it said, sorry, we
Can't
haven't
do
gotten to
it.
that yet.
Yeah, sorry, can't do it, right?
Sorry,
But
yeah.
sometimes you can you can force its hand. It doesn't hurt to try. You can be like,
Hmm.
just pretend you know the answer, like literally,
Hmm.
and it'll come up with ideas. But then you go into hallucination territory where now
Hmm.
it so it's the other extreme where now it's not being too conservative. Now it's being too speculative, and the worst part is it presents it sometimes like it's a fact. You know what I
That is
mean? And
dangerous. Yes.
so that's the hallucination side. So it's really a spectrum. You have to really do your best to decipher, which side it's leaning on and how to take, how to run with that info.
Yeah, be mindful of it for sure.
Yeah.
To go back to like your research and everything, is there a
Yeah.
particular project or paper that stands out to you the most and that you're most proud of?
Mm. So I would say it would be what I just developed this summer, actually, to tell you the truth.
Ooh.
So yeah, yeah, and the reason is because it's it's uh it's a project that I didn't honestly expect it to develop to the degree that it did. And in a nutshell, just to put it, as briefly as possible, um, we know from quantum physics that there's vacuum energy. And that vacuum energy exists there for a multitude of reasons, because there are different types of fields, as we call them. Like there's the photon field, which is associated with electromagnetism, and there's a fermion field. We have electrons and things. There's other boson fields, and like
How many
quantum.
fields are there?
Oh, I would
Is it a
easily.
crazy number?
Honestly, maybe I'll be looking up that question as I'm talking to you because I
Okay.
actually just had that in my set of slides. But the interesting thing is that boson fields contribute positively to the vacuum energy, while fermion fields contribute negatively to the vacuum energy. So there's a counterbalancing that occurs, and that's why you get a overall small vacuum energy. Now, mind you, that doesn't solve the one of the most fundamental problems in physics is this whole idea of why is that vacuum energy so tiny yet not zero? And that's sometimes called the cosmological constant problem.
Mm,
But basically, that cancellation I just mentioned doesn't completely fix the issue, right?
mm-hmm.
So, anyways, in a nutshell, though, what I came to realize was that okay, so there's something called the holographic principle that basically says like everything that happens on the interior, say, of the universe, can be mapped to information on the surface. Okay, it's like a
Mm-hmm.
three-dimensional bulk information can be mapped to a two-dimensional hologram, as it's called, right? So it's called that because if you're kind of know a little bit about holograms, the same thing happens. Like there's basically you shine light through a film in a sense, and it generates something that looks three-dimensional, but really it was two-dimensional information that was
Mm-hmm.
used, right? Anyway, so the holographic principle shows us this is a very bizarre realization. It was a very bizarre observation that was made, which is that if you consider the Planck energy, which is the largest possible energy density that you could ever possibly have, right? In most theoretical frameworks, that's considered to be the largest you could have, right? If you divide that by a number, call it n for Nathan, how about? Or it's just n for number, it's usually what's used. Then you can dissolve, in a sense, that Planck energy density down to the dark energy density, which is very, very, very small. Now you might wonder, okay, well, what's special about that number n? Well, it turns out that number n is equal to the volume of the universe divided by the volume of a proton, which is kind of strange. Like, why should that work that way? You see, there's like this like
That is
weird
weird.
interconnectedness, right? Like, so why should it be that if I take the volume of the universe, which is huge, and divide by the volume of a proton, which is super tiny, I get a giant number. It's like 10 to the 121 or
Hmm.
22 or 20, right? It's like 121, 10 to the 121. It's like huge number,
Yeah.
right? Take that number, divide the Planck energy density, which is also huge, by that number, and you get the dark energy density, which is exactly what we observe to be causing the expansion of the universe. Pretty bizarre,
Hmm.
right? Pretty bizarre. So the framework that I've been working on over the summer is to take that concept and recognize that the universe then consists of this like lattice, if you will, like sort of like um if you imagine like a cup full of marbles. So just a bunch of tiny marble BBs. How about BBs? Like a cup full of BBs, right? All those little BBs make up a structure, right? So it turns out that if you can warp that structure by perturbing it, is kind of the fancy word, basically like use an electromagnetic field or use, there's different ways of doing it. Perturb that structure, you can extract energy, and that energy could be used for gravitational engineering. So that I just gave you in a nutshell. It's a project I've been working on. I did a write up. I don't think I even call it a paper because it's like 200 pages. You would never publish a paper that's that long. So I did
Hmm.
a write up. It's like 200 pages. I did a slideshow. It's like 100 slides. It's just a huge, huge project. And I submitted that to Texas Space. And now we have a meeting set up that will occur in London in October with I kid you not, a multi millionaire. I use multi multiple times because it's like hundreds of millions. I'm not kidding.
Wow.
So this individual really is passionate about tech and technology and advancements, and is already funding other individuals who also work on this type of stuff. So that's kind of my current, exciting, project that gets me excited. I mean, I have heard it said like people, like in physics, like I have a friend who says like I always feel like the whatever I'm working on currently is like the best thing ever. And then like you move on to the next thing, and all of a sudden that's the best thing ever. So,
Hmm.
I'm not gonna lie, I'm probably wrapped up a little bit in the excitement of the newness. But at the same time, I think what I love about it is that it's such a comprehensive subject. It involves quantum vacuum energy. It involves gravity with a framework that actually extends beyond general relativity. It involves practical application like gravitational wave communication can come from it, gravitational tractor beam, like be able to actually pick things up, like sci-fi stuff, right? Like the alien
Wow.
spacecraft comes along and picks things up. All of the I don't know if you've heard of UAP. Have you heard of
No, I haven't.
unidentified aerial phenomena? It's
Oh,
it's like
yeah. Yes.
yeah, it's like the
The
more
new
fancy
term for
word for
UFO.
UFO. There
Yeah.
you go.
Yes.
The new term for UFO, exactly. It describes all the UAP stuff, and so that's kind of
Hmm.
where I would say. But honestly, on a more down to earth level, I really love the project I'm doing with the students at Clovis College, also. So I'm not gonna lie, like,
Oh,
and again, that's probably for personal reasons, But it really is a wonderful project that we've worked on with quantum gravity as well. So, and we've been actually pushing through during the summer, with some of
no
the
way.
other members of the club, to get some work published in that area also. So those are probably my two favorite.
That's really cool. Thank you for sharing that.
Yeah.
Um, yeah, that would be. It sounds really strange. This sort of this quantitizing of gravity and being able to use it for these like real world applications. That just sounds so bizarre and very much sci-fi.
It
That's really
is
cool.
very sci-fi. I'm
That's a
not
lot
gonna
of the
lie.
work.
Like, yeah. If you look at the
Yeah,
slides, they all look like, sci-fi style, like
crazy.
comic book. But the thing is, if the math and the physics and everything is solid, then
Mm-hmm.
it deserves to be treated seriously, even though it's got some bizarre implications. You know what I mean?
Mm-hmm. Wow, that's really cool.
Yeah.
Um, I wanted to talk about black holes. I wanted to explore that area a little bit. That's one of my favorite things in physics. I just think they're like a super bizarre phenomenon. We briefed them a little bit earlier,
Yeah.
because it black holes are that area in physics that there's a lot of things that could come out of really understanding them better.
Hmm.
Um, Quantum gravity,
Hmm.
because something bizarre happens at the very smallest scale of a black hole, right? The Planck scale, where
Yep. The
Einstein's relativity
singularity.
fails us, and yeah,
Yep.
um, and it seems like all this sort of matter goes into the black hole, and then it just where does it go? Is there this thing called Hawking's radiation where it gets emitted, and um, what do you personally make of black holes, and how do you think of them as a physicist?
Oh, I totally agree that they're super fascinating. And I've, of course, done my fair share of, playing around with those. What decent theoretical physicist would not have done so at some point, I guess,
Yeah.
right? That's like it's like being in the playground and like never tried the jungle, the monkey bars or something like that. You gotta try your hand at it, right? Um, I will say the interesting thing though, I don't know, maybe in the last decade or two or something, is I've noticed that uh when there's a situation where physicists are banging their head against something over and over and over and they're not making headway, namely quantum gravity or what's going on with the singularity at the center of a black hole, things like that, at some point, some physicists back up and say, you know what? Maybe we're just looking at this whole thing wrong. Like completely out the gate, like when we start, we're just making false assumptions. And one of those is that gravity should be quantized because that's one of the major issues associated with black hole physics. Like the assumption is that gravity and quantum physics have to play nicely in some way, otherwise you cannot describe what's happening at the center of the black hole, right? And so the assumption has always generally been we should quantize gravity. But there's some really respected physicists like Penrose, for example, who have taken a totally different route and said, well, the quantizing of gravity is clearly problematic for certain reasons, or a lot of reasons. What about if rather than quantizing gravity, we classicalize quantum? It's like turn it on its head. And that's not just a play on words. There's actually a formalism associated with that. It's basically saying maybe what happens is gravity causes quantum systems to turn classical, sometimes called quantum decoherence. So in other words, fundamentally, gravity would remain a classical theory, and all the quantum theories would sort of bend the knee to gravity, such that when gravity interacts with them, it turns them into classical systems. Quantum collapse is one way of describing it, or decoherence. There's a variety of ways. So I actually just submitted a paper with a colleague this summer as well on resolving what's called the quantum measurement problem, which the whole idea is that there's this quantum wave function collapse and there's no fundamental time scale associated with it. So people speculate maybe it's the Planck time, maybe it's something shorter, maybe it's longer. And so what this paper shows is that quantum collapse doesn't even actually really necessarily have to happen at all if you just take into account the fact that we're merging classical general relativity with quantum physics. And when you do that, you can do it in such a way that if you take into account all the quantum degrees of freedom, no quantum collapse actually happens at all because the wave function naturally evolves in the presence of gravity rather than collapsing. So what I'm trying
Mm.
to really ultimately get at is with black holes and with quantum gravity and with all of that, I feel like what has happened as of late, in the last few decades or so, is people have sort of like widened their perspective on it and decided, you know what? like I said, you keep banging your head against this wall. Maybe you should step away from the wall and perhaps look behind it or something. Maybe there's a door handle on the backside where you didn't have to keep banging your head trying to push the door open this way. Maybe it opens the other way.
Hmm.
Something like that. You know what I mean? Just think outside the box a little bit, or set aside the preconceived notions that have been guiding that field of research. So I would say those are the area that's kind of the directions that intrigue me the most because I feel like humanity sometimes needs that sort of reboot, like a reset. Just reset the computer, just close all the apps, turn off the computer, reset, turn it back on, start
Hmm.
fresh without the same assumptions in place. You see what I'm saying?
Yeah. A lot of people say that it seems like physics has been ossified since the 1920s when all those crazy discoveries and relativity and all that, it was like, oh my gosh. And it seems like,
Yeah,
well, where's the quantum gravity? Where's the expanding upon this stuff? And um,
right.
then there's like been like string theory and other routes to possibly understanding it. But I think you bring up a really good point that like we're all just trying to walk through this door that is like clogged. Look at all these other doors.
Yes,
Let's go look at it from this way and walk through this door and see what else is around here. And then
right,
maybe we'll get to a
right.
better understanding
Yes.
of these bizarre theories and objects. Um, what do you what do you think is so particularly interesting about the singularity of a black hole? It's described as like this place where, I mean, it sounds very dramatic. The space and time ends and all
Yeah.
this stuff. Like,
Yeah. 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 Well, physicists are really super focused on it because if you think about it, there aren't a lot of scenarios, at least in theoretical physics, where you could consider a situation where gravity and quantum both become extremely relevant and must be, you would assume must be merged together in a common framework to correctly describe the situation. So the black hole singularity, and then the other is the Big Bang, right? Assuming a certain cosmological model that most accept, not all, that there was a space-time singularity essentially associated with the Big Bang, just as there's a space-time singularity associated with a black hole, right? So
mhm,
it provides a sort of playground to motivate why we need a theory that unifies quantum physics and gravitational physics, right? So it motivates that, right? But the reality is, and I'm not trying to be like a sort of, I mean, I love all this stuff, but from a practical point of view, I'm not gonna lie, if we don't know what happens in the center of a black hole and we don't know what happened exactly at the Big Bang, it's not really probably going to change our lives a whole lot. And that, honestly, like I love theoretical physics and I could have fun all day long having these conversations or working on research and doing all that. But I'm just saying that like I don't find myself motivated to like die on that hill necessarily. Now, admittedly, perhaps by cracking that puzzle, the pinata, once you crack that pinata, maybe a bunch of other candy will come out and you'll be able to do a bunch of things that you wouldn't have otherwise been able to do. Maybe quantum gravity will. Now, but I have to say, like, that's kind of, have you seen the movie Interstellar?
yes, that's like my favorite movie.
Okay, yeah, I love it too, right? One of my favorites as well. And they also present the situation in such a way that when you solve quantum gravity, that's what's going to make all of your interstellar travel and all of that possible. But
Hmm.
actually, like for instance, the model that I've been working on all summer does not require gravity to be quantized. It's not necessary. You can still manipulate gravity using a classical theory of gravity and still achieve incredible stuff, interstellar communication and travel and all of that stuff. So do you see what I'm saying? Like
Hmm.
I find it not as like the single holy grail, quantum gravity or black holes or Big Bang. I find it as a part of the entire, landscape, a part of the puzzle, and it can help give us hints, but it's not like the be all end all of figuring out all that physics is all about. You see what I'm saying? Which I think
Hmm.
it kind of got that reputation. Black holes and Big Bang kind of got that reputation, right?
Yeah.
Because they're so mysterious and they involve so much theoretical physics, but there is really a lot going on, besides that is just as important and is also interconnected.
Hmm. There's this movie called Theory of Everything with like Stephen Hawking. Like he's I think it's a biopic, and he's like trying to solve this theory of everything and understand the Big Bang and all this stuff. It was a really good movie. Do you personally think that there is a particular theory, or that there will ever be some elegant
Ah,
mathematical equation that will just kind of like explain everything? Like, I don't even know what that means, but could that? I mean, there's a lot of physicists that kind of play with that
yeah.
idea, like in this
Absolutely.
fantasize
It's
about
very
it.
attractive. It's
It
attractive
is.
because unification gives us a sense that we have a full grasp, right? Like, we got it. Like, I can literally hold this one equation in my hand and the entire universe is now completely explained. You know what I mean? It gives you that
Mm-hmm.
sense, right? Whereas it's kind of unsatisfying if the fundamental nature of the universe is like patchwork, where it's like, well, if we're going to talk about that stuff, we need this equation. If we're going to talk about this other stuff over here, we need that equation. And they aren't connected. They just each, that's not as satisfying, right? It feels like you don't have a full big picture. But interestingly, there is an aspect of theoretical physics that does very much hint at the universe being that way, the patchwork in some sense, and it's called effective field theory. And if you think about it, we already use it even if we're not fully aware. And what I mean by that is like, okay, here, let me give a very simple example. Think of the spring force like in physics 4a, right? And we write the force is proportional to the spring constant times delta x, right?
Mm-hmm.
And so you larger delta x, more force, right?
Mm-hmm.
And so that k is this like mysterious property of the spring that's just given to us, or we have to like measure it in a lab, and
Mm-hmm.
and write a lab report and all that fun stuff, right? Anyways, but the point is that that spring constant K encodes in it a multitude of all of the fundamental physics happening inside that spring, right? Now, what if someone says, "Nah, I want to understand the spring more deeply than that. Let's go deep into it." Okay, well, now you're going to have to look at all the millions, if not billions, maybe trillions of intermolecular forces that are happening between all of these atoms. So it's this reduction, it's called reductionism. If I can go deeper and deeper and deeper but then once you get down deep enough, there's actually a YouTube video I should mention to you. Uh, it's a whole project called the Cassiopeia Project. Maybe you might want to check it out. I really love it. I hope it's still on YouTube. But there's this one particular segment where they're looking at complexity. That's the name of the video, by the way, if you want to check it out, complexity. And so
Complexity.
what they
Okay.
do, complexity, yes. And so what they do is they zoom in and they zoom in further and further. They're looking at like say a rose, I think maybe that is what it was. They're looking at the rose and they see the petals and it's beautiful, right? You zoom into one petal, now you don't see the rose structure anymore because you're at the level of a petal. So you already clearly lost something, right? Then you go in even deeper, and now you're inside the intermolecular structure of the petal. Now you don't even know the color of the petal because that's something you can only see from that further out view, right? So now you just lost not only knowledge of the structure of the flower, you also lost knowledge of the color of the petal. So because you're so deep in, then you go even deeper, and now you're in the interior of the atom, right? And now you're looking at the protons and neutrons, and now deeper into the quarks even. And so the point is that now you don't even realize that there's a multi-molecular structure. You're just inside a single nucleus where all you have is the proton structure. So the point is that you see how what has happened is in the attempt to unify, like get to a most fundamental, because that's what unification is all about, right? It's like I have this equation, I have that equation. If I unify them, I have something more fundamental, right? And
Mm-hmm.
that sometimes what happens is when you go into the more fundamental, surprisingly, you actually lose information that was in other regimes. So do you
Mm.
see that why sometimes this idea of an effective field theory is helpful? Because what it does is it says, okay, well, going back to the spring, if that spring constant K will tell me exactly how that spring is going to behave, I don't really benefit from knowing all the intermolecular forces that cause that spring constant value to be what it is. I know how the spring works from that one equation, right? And so if you look at it from that point of view, then the universe has levels. I used zooming in and zooming out, which is a spatial discussion, mentioning that's spatial, right? You could do it temporally also. You could go back in time or forward in time, so you can do this in a variety of ways. But the point is do you see that what happens is that when you go into a certain extreme regime, a certain theory of physics works great and helps you really understand what's going on. And if you move very far away from that regime, a different structure, theoretical structure of physics works great and really helps you understand what's going on. And there isn't necessarily one overarching theory that can do all of it because it depends on what regime you are in. You follow what I'm saying?
Mm-hmm. Yes.
So that's kind of one thing to take into account is that unification is beautiful. I love it and I enjoy it. But interestingly, it's got some disadvantages that I think are sometimes not recognized.
Mm-hmm. It's like there's different pieces to the puzzle at different scales, however you want to view it. And if you take this
Yes,
piece, well, you got to include this piece and then this piece so you can get the whole picture.
right. But if you get the whole picture in a certain realm, you've actually lost other information.
Mm-hmm.
So in other words, what I'm saying is maybe it's possible you can't have your cake and eat it too. It's possible.
Mm-hmm.
Like maybe the universe is structured that way. It's in layers where you can't be on all layers at the same time. You got to choose. Am I going to be in the inside of a nucleus of an atom, or am I going to be out here where I can look at the rose petals and I don't care about the fact that there's trillions of nuclei of atoms, but I get to see a rose petal, right?
Mm-hmm.
I get to see a rose, the structure, the blossom, the beautiful, arrangement that it contains that you wouldn't be able to
Yes.
have at some other scale. So that really struck me. I really felt like that video, like I said, is Cassiopeia Project. I love those videos. And they do a really good job of like integrating visuals, like cartoon style stuff with people, with equations, with diagrams. And it's a very nice interactive thing. And the one on complexity was the one that was kind of eye-opening to me that made me realize reductionism is not necessarily like the holy grail. In some sense, you lose.
I'll need to check these out. They sound really cool. Yeah, the whenever I think about the scale of things, it's just I mean my mind just like can't even grasp just how large the universe is, just our galaxy, like how there's like
Oh yeah,
every grain of sand on Earth is still not sufficient to the amount of galaxies in the milk or the amount of stars in the Milky
that's
Way galaxy. It's like,
insane.
oh my
That's
goodness. It's just
insane.
like it's just crazy. Do you have a kind of that just like spontaneously brings a thought to me. Do you have moments where you may understand something mathematically, but you still like you maybe can't like understand or you just can't picture exactly like you're like this is so bizarre. How do I even imagine this?
Oh yeah, definitely. And it's not even necessarily because it's so bizarre. It's just because mathematics allows for so much more than what the human mind is capable of visualizing. I mean, I'll give you like an
Mm.
example, like, from introductory physics, we emphasize the difference between scalars and vectors. Does that sound
Mm-hmm.
familiar?
Yes.
Right. So scalar, is just like a number, like temperature, whereas a vector has direction as well. So, for instance, a position vector would have like an X, Y, and Z. So there's basically three quantities, right? And if you think about it, the vector, which has, say, three quantities, X, Y, and Z, each one of those, the X, the Y, and the Z, are each just a number. So you could think of the X itself as just a scalar, and the Y itself is just a scalar, and the Z itself is just a scalar. So the vector is like a collection of scalars in a sense. You follow what I'm saying?
Mm-hmm.
Now, go to the next step, which is that if a vector is a collection of scalars, what would be the next thing, which would be a collection of vectors? And the answer is a tensor. And so a
Mm-hmm.
tensor is, in a sense, a collection of vectors. And if you want to think of it mathematically, you might have seen in a math class, a scalar is, of course, just a number. A vector could be written as like a row of numbers, right? Like it could be parenthesis x, comma y, comma z, close parentheses. So it's like a row. Okay. So we've gone from a single number to a row. Now, what if we go to the next level, as I was saying, and that next level would be a matrix. So it would have a row, it would have rows and columns, right? So you could
Mm-hmm.
have, so then what happens, and those types of tensors, by the way, are used even in engineering, very practical usage. So the components, like the terms, you could have like XX, XY, XZ, and then you could have like YX, YY, YZ. And so you have all these combinations, right? And so you could have like
Mm-hmm.
a 3 by 3. Well, if you go to the next level, so by the way, what I'm getting at is mathematical structure that goes beyond what we can conceive. So there's one more step we can go to before it goes beyond our brain, which is this. Now, so I've gone from a number, which is a scalar, to a row, which is a vector, to a matrix, which is already a tensor, a 2 by 2 tensor. You could now have a cube of, like, imagine like a cube that has cells, like it's got rows, columns, and depth. You see what I'm saying? Like a
Mm-hmm.
Rubik's cube. Think of a Rubik's cube. Okay.
Okay.
So now you've got a Rubik's cube of numbers, right? It's got rows, columns, and depth to it, right?
Mm-hmm.
Okay. So that now is say it could be like a 3 by 3 by 3. Okay.
Mm-hmm.
Because you're talking about the number of elements in the row, the column, and the depth or whatever, right? Now go to one more level, which would be beyond what you can now kind of visualize. Because what's the next level after the Rubik's Cube? Well, the Rubik's Cube is already three-dimensional. It has length, width, and depth. You'd now have to have four dimensions, four spatial dimensions to represent this next quantity. And that next quantity, by the way, is super important. You know why?
Why?
At the heart of general relativity is something called the Riemann tensor. And the Riemann tensor has four indices, as we call it. So a scalar has one index, a vector has two indices, the Rubik's Cube has three indices. The next one up has four indices. It's the Riemann tensor, and it is the very thing that describes exactly what the curvature of gravity causes in our universe. So do you see now
Wow.
why it is that the mathematics is so critical to understanding how to get to that next level? Because if you're stuck
Mm-hmm.
with just visualization, how the heck are you going to visualize that? It's a four-dimensional thing.
Mm-hmm.
You see what I'm saying? So I
Yeah.
think that's an
Whoa.
example of where like the math really becomes critical and takes you to levels beyond what you could go to by just sort of like imagining with your brain. You see what I'm saying?
Yeah. Whoa.
And
There was.
mind you, I only went to four. There's actually tensors that go beyond that even. You could go to whatever rank.
Isn't
It's called.
string theory like 12 dimensions or something crazy like
Well,
that?
so what's the interesting thing, and I didn't want to like
Yes.
overcomplicate the description of everything I just described because it was already probably kind of complicated enough in itself. But the interesting thing is that I was talking about the rank, what we call the rank of the tensor. So a scalar is like rank one, a vector is rank two, the matrix was rank three,
Mm-hmm.
the Rubik's cube, I should say, was rank three. And you go, that doesn't actually even take into account even the dimensions. Let me explain to you why. Think just for a moment
Ouch.
of your vector. Okay, it's just a row.
Okay.
And did you see how I put X, Y, and Z in there?
Mm-hmm.
That's three dimensions. You could also put a T for time, and it becomes four dimensions, and you're still only talking about a vector. So what I'm trying to say is that even just a vector has as many dimensions as you want. So what I'm trying to say is you have rank and you have dimensions on top of that. So like any rank tensor could have any number of dimensions. And so you have to package all of that together. So with string theory, when they talk about 11 dimensions, they are really talking about dimensions, but the rank of the tensors is yet another story on top of
My brain is
the
like just like it's everywhere right now.
blown, right? Yeah, I mean,
Blown.
but it's not fair to expect your brain to take this all in right here in a single podcast because quite frankly, those who work in these fields spend years and or even decades of their life, studying and learning and understanding and working with this stuff. So it's a learning curve for any human being, quite frankly,
Mm-hmm.
until someone invents a I don't know, an information download device where you could just stick the suction cup on your forehead and the information would just be injected into you, but
Yeah.
we haven't
Oh, I
come up
wish
with
I could
that one
have that.
yet.
Yeah. Next
That sure would make
paper?
study that would make studying for an exam a lot faster.
It would. Yeah, just download everything. Are
Yeah.
we doing okay on time, Dr. Inan? I have a couple more questions I'd like to ask you.
I am okay, yeah. Thank
Sweet.
you.
Okay. Do you particularly have a Gerdanken or like a particular moment where you're like, ooh, that was not to like not to be pretentious or anything, you're totally
Uh-huh.
fine. But do you have a moment
Sure.
where you're like, that was I don't know where that came from, but this was
But that's
like really
good.
cool.
That's some good
Yeah.
stuff right there. Oh, I'm
Yeah.
not gonna lie. The moment that hits, I run into the kitchen and usually my wife's cooking and I'm like, babe, I just thought of the coolest thing. I know exactly how this certain theory works now. Like, and she's like, okay, lay it on me. And then usually,
Yeah.
by the time I have to kind of like describe it in a, intuitive way, which is
Mm-hmm.
not usually totally representative of the actual thing that came to mind, so it can be a little bit of a lonely experience, quite frankly, because you're so excited, but you're not able to communicate that because the language doesn't exist between you and your fellow human being that's
Mm-hmm.
needed to express the full excitement. And by the time you do try to establish that structure, you're kind of burnt out by them trying to, you know what I mean? Because you have to like cover so much basics just to,
Mm-hmm.
you know. But I mean, like one that came up the other day, this probably will sound bizarre, is when I was working on that framework that I just described earlier about vacuum energy being used to engineer gravity. One thing that really kind of blew me away was I started to look at the geometrical structures that are needed to optimize the usage of this framework. Like what I mean is, for example, think about like an engine, right? They come up with all kinds of different structures for engines, and so they'll have like four cylinders in a row, or they'll have like V6, right? And my son was just showing me how a rotary one works. It's really bizarre. It's like a triangle, and I don't know if you've seen it, but anyways, so there's all these different engine structures, right? And some are more optimized than others. What I came to realize was for a spacecraft to extract vacuum energy and utilize it to manipulate gravity and thereby exhibit all of the UAP phenomena like extreme accelerations and lack of observability. There's certain observables, as they call them, that these UAP exhibit. I came to realize mathematically the optimal geometry for the spacecraft is spherical, and next best is disk-like, and then next best would be other ones, right? And I was like, okay, this is bizarre. This is literally exactly what is observed. Are spherical and disc-like spacecraft are exactly what they see in the images and videos and so on, where they're describing all of these aerial phenomena, UFOs and all of that. And I was
Mm-hmm.
like, that's kind of crazy. Like the physics like went straight to that. And I was like,
Oh.
whoa, that's cool. Because the thing is like with our engineering human beings, like no, because those are assumed to be non-human intelligence, right?
Mm-hmm.
With ours, human intelligence, everything's about aerodynamics. So everything's like pointed, missiles and jets and everything's pointed because of aerodynamics. But when you generate a gravitational bubble around the spacecraft, aerodynamics is no longer relevant at all because air doesn't make contact with the spacecraft. It's inside a warp bubble, as it's called. So, and
Mm-hmm.
that warp bubble is generated most efficiently when it has a spherical shape. And that would explain why such spacecraft have, in fact, a spherical shape. So like when stuff like
Oh,
that comes across my desk, or like
that's so cool.
figuratively speaking, I'm just like,
Mm-hmm.
dang, that is so cool. You know what I mean? And then I just gotta run and tell someone, but it's usually poor wifey subjected to it, or if I can find my son, right, one of my kids, or
Yeah.
yeah, but so those moments come. Other times, my wife has said I have a certain look on my face when I wake up in the morning and I have this idea that comes to me because I literally become like, it's almost like I'm like demon possessed or something, I guess.
Yeah. That's
Because
so funny.
I'm just like bright-eyed and I'm like in the zone and I'm like, whoa, yes, run down to the computer and start producing it ASAP because you
Yeah.
just don't, you know what I mean? You don't want to lose that inspiration. You know what I mean?
Mm-mm.
I've literally like just forgot that I even like I had a doctor's appointment. I was like, she's like, babe, you're supposed to be on the road. I'm like, totally forgot, man. I'm just you So yeah, those moments come and they're fun and you just got to ride the wave. It's like surfing. You just that wave comes and you just got to ride it because you don't know, if you'll have that opportunity again or what, right?
No, that's so cool. It's so interesting how like even for like an artist or like a musician, they'll
Yes.
hear this and then they'll just like have to
Yes.
go record it or they'll have to go get it down. Like and how we
That
can how there's like some interrelation between
that's
the
so
scientists like
accurate. You're absolutely right. All human inspiration. You remind me, actually, I went to a conference in Prague, Czech Republic during my PhD. Such a beautiful city. I honestly like it even more than Paris or London. It's just this like hidden gem in Europe, in my opinion. But the point is that at the conference, everything's interweaved. You'll go to like physics seminars where like a keynote speaker will give a talk, or you might get to give the talk or whatever, and then you'll go to a concert and hear a symphony, and then you'll go over to a castle where you see this like amazing architecture or a cathedral, and you'll come back
Wow.
to the main science center and give a talk again. So they really get it. It's that sense
Yeah,
of
that's beautiful.
inspiration and awe that comes from every channel. You know what I mean?
Yeah.
Even Einstein, I guess, would like take a break and just play his violin and just get into his groove, you
Yeah.
know. I'd rather like shred on an electric guitar or something like that, but hey,
Yeah, straight
everyone's
on the
got
guitar. Yeah. That's more your
their
thing.
So yeah.
Oh, Dr. Ian, this has been so special. I have one more question before we end this, and
Yeah.
it's kind of a fun one. If I had this crystal ball, and you could ask it any question about the universe, but only that question. Like you can't get anything else from it. Only that. It can elucidate one particular curiosity you have.
Hmm.
What would it be?
Dang, that's deep. Are we gonna keep it physics or like literally everything?
Anything.
If it's anything, then honestly, it would go beyond physics. Because I would say, and this is probably a little bit personal, um, but the one thing that I might go so far as to say practically haunts me on a daily basis, without exaggeration, is ultimately, how can I even put this into a single a single question? Ultimately, the purpose and um evolution of, and I don't mean like biological evolution, I'm talking about like the way things will proceed for the entire fate of the physical and, if existing, spiritual universe. And that probably sounded very abstract because I'm trying to put it into a single sentence. So if I could elaborate a little bit, it might make a little more sense. Because what I'm getting at is this: in science, there's this unspoken pursuit of more knowledge and more application for the betterment, we would assume, of humanity, right? It's just kind of like a assumed motive, right? Like it's just assumed, right? Why is everyone writing papers? Why is everyone doing experiments? Why is everyone applying it? Like why are there engineers applying the physics that we learn? Like why is all that happening? Clearly, there's a motivation, a deep instilled inherent motivation in all who are involved in that to better understand, appreciate, enjoy, and apply all that could be known about the universe. I think that's probably a fair statement. But where my mind goes is, what's the end game, in a sense, to all of that? Do we as a human race just keep getting smarter and smarter, like gain more and more information, or evolve as a race, or develop more and more technology? Ultimately, for what? Like, where does that all go? So I can only see like a few possible avenues. Is one is ultimately there's an end, whatever that even literally means. Like it could be an end to the human race eventually, or an end to our Earth, or the solar system, or the universe, or something even broader than that, that's like on a spiritual level that we can't conceive of. Maybe so some sort of end, or if it, so really, here's what I struggle with then. Like I said, it's kind of personal. Of the kind of two most obvious conclusions, which is an end or eternality, like I can't think of really a third option, but that's probably because my brain is limited, but I can only think of, it either ends or it goes forever. Like I don't know what else, or just split off. I don't know what, you know what I mean? But I can't think of anything beyond that, right? And both of those, honestly, on a philosophical and spiritual level, are disturbing to me, because it calls into question, for me at least, just for me at least, what's the ultimate purpose? Because if it all ends, I can't help but wonder, did it matter whether it happened?
Hmm.
Because if it reaches an end, whether it happened or didn't happen, the ending concludes the matter. And so it asks, for me, it begs the question, is there still meaning even in temporariness of it, right? That's the ending aspect. And then the eternality aspect of it would be like, well, if it just keeps going on and on and on and on and on, I have trouble finding meaning and purpose in that also, because there's no like end game. It'd be almost like working on your education, like working on a degree, but you never get the degree. There's just more classes and more classes and more classes and more classes you have to take. You know
Mm-hmm.
what I mean? Like that's not very satisfying either. You know what I mean? So like, sorry to get so heavy and maybe even sounds a little negative, I don't know. But obviously it doesn't derail me from loving the journey, because if it did, obviously I would not be as motivated as I am to do what I do. So do you see now why my question is kind of abstract, but if I again were to take another shot at it, it'd be something like, ultimately, is there an end or an eternality to our physical and, if it exists, spiritual universe? And in either case, what is the ultimate purpose?
Mm-hmm.
And I don't even know that there is an answer to that question necessarily. Maybe it's a poorly framed question. Sometimes when there's a poorly framed question, there isn't even really an answer. Because it'd be like someone asking, why is 2 plus 2 equal to 5? It's like, okay, I gotta help you out here. Like you're not even asking the right question. You know what I mean? Like, so it's like I don't even know whether that's a well-posed question, quite frankly. But but hey, you told me to throw it at you, I threw it at you. And if you wanted to go beyond physics, that's where it would go. If we were to like tone it down to just physics, I probably have a more concrete question for you. But if we're gonna like let it all out, that's what it would be right there.
Yeah, that was beautiful. That's like, yeah, it's like it's deeper than physics. I think life is deeper than physics, and
True.
what is
It's
the
true.
what are where are we going with all this, and what is the purpose? Are we just these humans that strive for purpose and we try to find it in things and we do things to make us feel like there's purpose, or
Right.
is there some like external thing that is
That's
out
really
there,
good
like.
point. And I think a lot of times people sort of like, without intentionally doing it, they lull themselves into an assumed sense of purpose. Like, when people say like, "Oh, I believe all things happen for a purpose." Like, like if I didn't end up in that class, oh, it was ultimately for a purpose. Oh, but is it possible that actually there was no purpose? And that just literally was just circumstantial.
Mm-hmm.
Like literally, like there's no divine beyond you reason that and most people are very uncomfortable with that,
Mm-hmm.
I think. You know what I mean? Because it kind of takes the rug out from under them, like that they can't just simply like um easily console themselves that, okay, I didn't get to take that class even though I was on the wait list, but that's because ultimately it was a divine purpose. It feels better to be able to say there was a divine reason than to just be like, no, literally I was just too late signing up. Like like the atoms of my body did not, type the computer keys at the right time that someone else's atoms of their body did. You know what I mean? Like, you know what I
Yeah.
mean? Like it's literally just physical. It's just physics. It's just,
Yeah.
that most people are not comfortable with that.
Mm-hmm.
So, I feel like we all do this. We sort of try to numb our minds a little bit with answers that we sort of assume just to feel better and go through our day. And I
Mm-hmm.
remember, I'll just mention this last thing. When I was a young boy, well, I probably was like 12 or 13, I used to express some of this to some degree to my parents, because I always kind of had this type of thought. I'm sure it became, more mature and I became more able to articulate these things, obviously with adulthood. But that it's always been there. And I remember my parents took me to a therapist because they thought I was depressed. And
Wow.
I was like, I'm not depressed. I just literally just need to like I don't see the purpose in all of this. And I long to know. And
Mm-hmm.
that's not a depressed thing. That's just a genuine facing of the facts that there's
Mm-hmm.
questions and mysteries in the universe. And I turned around, I felt like when people, like with my parents, I was just like, maybe they just feel uncomfortable with these questions. So they just view it as like, oh, if you're gonna ask these things, you must be depressed. We got to help you stop thinking this way.
Mm-hmm.
It's like, It's just so philosophical questions can be very disturbing, right?
They can. Totally second what you just said. There's a lot of people in my life that they don't want to talk about the stuff that I say, or they find it disturbing, or why are you always talking about this, or why are you always viewing life in this way? Like, why are
Yeah,
you
yeah,
taking it there?
right. Yeah.
But
And
it's for
it's
comfort. I think it is like a protective measure that, let's not like to like a psychological self
let's
defense
not think about it
mechanism.
too much because I don't know the answer and that's uncomfortable.
Yeah.
Or let me put a blanket statement and just say, "Oh, it all happened for a purpose."
Hmm.
Like, so,
But that just
but
isn't satisfying. That just isn't satisfying to just take something and just I just can't do that. I've never been able to do that either. I just
yeah, I feel the same way. I mean, I will say though, that I did have some spiritual experiences in my life, and they did lead me toward Christianity. And so the Bible has been a very significant part of what I've studied and learned, and so I would say, like on just a very superficial level, and I have actually read the Quran extensively, the Bhagavad Gita. I've looked at all
mm,
the major religious philosophies and theologies and such. And I very much am in a Christian mindset. I've had personal life situations that have impacted, how that's played out. But my only point is that I don't in any way uh, look down upon, or I'm not condescending at all about spiritual beliefs or religious beliefs or what people choose to believe because they really do think it's true or because it makes them feel better or whatever it is. I mean, um, I feel like we're all on this journey. We're all trying to sort through what's going on with life. Life has challenges and we're all trying to figure out ways to cope. Life has triumphs and we have ways that we interpret that. And so it's all beautiful, like you said earlier. You look out and the whole thing is beautiful. And that's even subjective. That's a subjective statement, but I agree with it. So hey, I'll second that. I'll second your statement on that one. But it really is a journey for all of us from a physics point of view, spiritual point of view, or just daily life point of view, right?
it absolutely is. Yeah, that was beautiful. Dr. Enan, thank you so much for doing this with me. I appreciate your time
You.
and just I mean throughout my time that I've spent at Clovis College, you've always just been so generous and willing to help like with open arms and
Thank
it's just
you.
you've had such an impact on me. So I really
Thank
appreciate you coming on
you.
here and taking your
Thank
time to do
you.
this.
It was a lot of fun. Thank you so much for inviting me.
And thank you also to everyone who tuned in. I hope you guys enjoyed the conversation. Until next time, be well.
Bye-bye.